Today I will be presenting from forest types to trees, a web-based digital twin of individual trees using OGC 3D tiles. Before I begin, I want to ask one question. Is it possible to create a large forest down to each individual tree as a digital twin on the web? We asked ourselves this question and we decided to try it. The answer is simple. Yes, it works very well. In this project, we converted the Korea Forest Service forest time map into OGC 3D tiles for a web-based service. Instead of using only general forest polygons, we focused on each tree, its spaces, height, and crown diameter. Many people think this level detail is too heavy and too complex to show on the web, so we wanted to test that idea. We built 3D models of real tree spaces and placed each one in the correct location with the right height and size. These are not simple symbols, they are trees that look close to real ones, and the result it runs smoothly in a web browser. Now let's take a look at today's agenda. First, in the introduction, I will explain why we chose the topic from forest types to trees, the background and motivation of our project. Second, data source and pre-processing. I will introduce the nationwide forest time map of the Republic of Korea that we used and explain how we prepared and cleaned the data. Third, 3D modeling and I3DM generation. I will explain the technical steps for creating individual trees and converting them into 3D tiles. First, visualization. Web-based digital twin, you will see how the system actually works in a web browser. Fifth, integration into the platform. I will show how this work is connected to our wildfire spread prediction system, which is currently under development. Sixth, in the future work, we will talk about possible improvement and next steps. Let's begin with our first topic, is introduction. We are currently carrying out an AI-based wildfire spread prediction research project led by the Korea Forest Service. Our goal is to predict wildfire spread and show the result on a 3D web-based map platform. Most existing platforms use the forest time map as 2D vector data provided through WMS service. This is fine for general forest management, but it cannot show individual trees, which are very important for accurate wildfire modeling and for building a forest digital twin. However, information at the individual tree level, such as spaces, height, and location, is essential for precious wildfire spread prediction and for managing digital twin forest. To solve this, we created 3D models of individual trees based on the forest type data and visualized them on the web using the OGC 3D tiles standard. Now let's take a look at how we made this possible. To understand the technical background, let me first explain what I3DM is. I3DM, or Instanced 3D Model, is one of the tile formats in the 3D tiles specification, which is an open standard defined by the OGC. It's a data format that supports GPU-based instancing, which means it's very efficient when the same 3D model need to be repeated many times, even millions of times. The main idea is simple. It allows one model message to be rendered multiple times in the scene using different transformation data and attribute information. This makes it possible to render large-scale 3D data very efficiently. For forest, this is especially useful. Instead of rendering millions of trees one by one, we can prepare a few tree models and repeat them using instancing techniques which greatly improve performance. Now let me walk you through our data processing flow. We processed our data using Mago 3D Tiler, an open source tool developed by Gaia 3D. We selected this tool because we need two custom functions. First, the ability to generate individual trees. Second, the ability to divide polygon-based forest time maps into grid and extract points and assign them to individual trees. Since Mago 3D Tiler did not originally support converting polygon data into i3DM format, we developed this feature ourselves while moving forward with this project. Our processing workflow works like this. First, we divide the input data. The input data is the forest time map into 5 by 5 kilometer grid units. Then we tile each grid separately. Finally, we merge all the tiled results back together. With this divide, process, and merge approach, we were able to handle large-scale nationwide data efficiently. This workflow allowed us to convert Korea's entire forest inventory into a web-based 3D digital twin at the individual tree level. Let me introduce the data set we use. Our data set is the nationwide forest time map of the Republic of Korea, provided at a 1 to 5,000 scale. In terms of file format, it is polygon data in GDB format. GDB format is the ArcGIS geodatabase format, and it contains about 3 million polygons. Key attributes include tree species code, forest age, tree height, density, and several other properties. This data set is the official forest information provided by the Korea Forest Service, and it offers detailed coverage of all forest areas across the entire country. Before we process our data, we need to perform some pre-processing steps. First, format conversion. The original data was in GDB format. We converted it to GeoPackage format using QGIS. Why did we do this? Because GeoPackage is much easier to work and fits well with our open source workflow. Second, we did spatial division. To handle this large data set efficiently, we split the data into 5 by 5 kilometer grids. This grid-based approach was important for converting the data into 3D tiles in an efficient way. By dividing the entire country into smaller grid units, we were able to process each part separately and then merge everything back together. However, we faced a major challenge during pre-processing. At first, we tried a simple method without changing any code. We tried generating points in QGIS and then converting them. But soon we found a serious problem. South Korea has about 7.2 billion trees, an extremely large number. When we calculated the data size, we realized that 7.2 billion trees, using only 12 bytes per tree for XYZ coordinates, would OLED be about 86.4 gigabytes, and this is only for position data. If we also include attributes like species, height, and density, the data size becomes impossible to handle. Because of this, we need a different solution. This is why we decide to modify Mago 3D Tiler directly. Now let me explain how we generated individual trees. First, the tree placement strategy. We placed trees using probability within each grid cell. We used randomized placement method, but we apply a probability distribution based on the forest density so that the number of trees match the real condition. Next, instance scaling. Each tree instance is scaled using the density and tree height attributes. This allows us to show forest structure that are close to real-world patterns. Finally, performance optimization. For performance, we used a special approach. Instead of the traditional LOD system, we applied distance-based step-by-step loading, where trees are added depending on the distance between the camera and the tiles. To do this, we set the refinement type to add, meaning additional trees are loaded as the camera gets closer to a tile. With this trade-off, we were able to achieve better performance. Now, let me explain how we actually generated the 3D tiles. We modified the source code of Mouse 3D Tiler to support polygon-based I3DM generation. This allowed us to directly convert forest polygons into individual tree instances. The main parameters used in the generation process were height, scale, density, and heading. By using these, we could accurately capture the characteristics of each tree. After learning this process, it took about 1 week to build the entire dataset. In the end, this generated roughly 450 gigabytes of tile. Let me explain how we prepared the 3D tree models. We handcrafted lightweight 3LB model for each major tree type. We created 4 categories: broadleaf trees, coniferous trees, mixed forest, and bamboo. For this project, our focus was on large-scale data visualization, so we did not use LOD at this stage. Instead, we chose a strategy that prioritized performance over fine details. Here's our final result. This is a real forest data shown in a web browser. Each green dot is one tree at its real location. This is real data from Korea Forest Service. And this is a demo video. This is a forest area in Korea. You can see the forest from far away. As I zoom in, trees start to appear. They load step by step. Getting closer now, more trees are loading. Each tree is a 3D model. Now you can see the thousands of trees, but it's still smooth, no delay, no freezing. This is running in a normal web browser. As we move around, trees load and unload by themselves. The speed stays good. This shows millions of trees in real time, all in a web browser. No special program needed. Now, before showing the actual visualization result, let me explain the static testing we conducted. To check accessibility and geometry accuracy, we tested the system under various conditions. We used Chrome DevTools to apply network throttling and simulate different network environments. For example, we used FOSS4G, which represents the slowest acceptable mobile network standard in Korea. This was set as our minimum baseline. The hardware we used for testing was a standard high-performance PC, and the software environment included Chrome browser, Cjm.js, and Mouse 3D. For network throttling, we set FOSS4G. We also disabled browser cache and content encoding to ensure consistent test of result. Now, here's the most important part. Let me show you the demo applied to our actual platform. One you are seeing is the 3D visualization of our wildfire spread prediction system, which is still under development. We have set up a scenario where the wildfire occurs near Daegu in Korea, and And the system shows a real-time spread prediction. The key feature to notice is the individual tree visualization. As I zoom in, you can see trees appear progressively based on distance. Along the wildfire path, you can clearly see which trees are actually in the area. Also, because we use different 3D models for each tree species, you can easily distinguish between coniferous and broadleaf trees. The most impressive part is that all of this runs in a web browser. Without installing any software, we can serve the large-scale individual tree data quickly and smoothly. As we conclude this project, let me share our future improvement directions. First, data refinement. Currently, we use representative tree models, but in the future, we plan to differentiate models by detailed spaces. Second, LOD system implementation. Instead of the current low-poly flat rendered trees, we plan to use complex original tree models with automated billboard-based LOD. This will allow detailed model to appear up close and billboard at far distance, further improving performance. Third, 3D Tiles 1.1 integration. By adopting 3D Tiles version 1.1 and using GRB custom attributes, we can control and query individual tree objects more precisely. With these improvements, we aim to build a more refined and efficient forest digital twin. Now let's move on the question and answer session. Unfortunately, the developer who led the technical implementation could not join us. So if you have any technical question, please feel free to contact by email on magus3d@gaia3d.com, or you can create an issue on our GitHub repository at follow links. We will respond to your inquiries promptly. Now, this concludes my presentation. Thank you for your attention.
Thank you, Eden. That was fascinating. Seeing the trees individually like that has many implications for managing landscapes and fires in response. That was just very fascinating. Are you open to any questions, or would you like them to be directed as you just... Are you open to questions now, or would you like them to be directed as you said there?
No.
Now, you would. Okay. Does anyone have any question? Okay, we see one here. Run this up. I guess I'm closest.
Nice presentation. I wanted to ask, are you using, up here?
Oh, sorry.
Are the trees just for the visualization, or are you actually using the individual locations in some analysis as well?
Thank you for asking. So it's hard for me to explain this in English right now. So can I explain it to you again after this?
Well, not in Korean.
Oh, yeah. We need to transfer.
Okay, we can talk, later.
Yeah.
In the attributes that you brought through, so position and height, you included heading.
Sorry?
You included the attribute heading or direction. Can you explain why that's useful? In the tree attributes, so each tree knows its position and its height and its type, and also its heading, I think it showed. Yeah. Can you tell me why?
Hidden? Oh, it's too typical question. So I think the attribute need to tile the 3D model. So if you have any detail, if you want to get a detailed information, please send, please GitHub issue. Sorry.
Okay. 감사합니다.
Anyone else? Okay, well, let's give another round of applause for Heejin.
Thank you.